To conclude the course, let me just simply consider the last one, the last one, type of the integrals, and we'll try to give you an example, and that's it. And we will be just waiting for the examination. So type, I think it is 4. Sorry. Type number 4 of real integral. So let's consider this integral. This is again an improper integral, a little different. That's why we are doing it, just to show you that these methods can be actually custom made for specific integrations, for specific types of integral. And it will be possible, it is actually possible to, let me write it down, this will be f of x dx, and like it is done here. So here we assume the following. So first assumptions A. So here we have here that f of x is again a rational function. So this is p of x and this is q of x. So basically we just want to have finite number of singularities. That's why we are putting this like that. And then of course we will also assume that a, b, so this is my b, that a is not an integer, so this is not equal to any of those numbers, so that means it's not equal to 0, plus, minus 1, plus, minus 2, etc. Otherwise it would be the same, type of the integral that it was in the type number 2, and we already covered it, so there is no need. And finally, two more conditions. We also will have that f of x, which is a real function, so we will be positive. So it is positive for, let me check it. Let me check the assumption. Actually, not really. So let's write it down. We'll find out during the process. We'll figure out this is a positive for x being a positive number. So we do not exclude that 0 is a singularity here, C and D. And finally, we have the last assumption. Means in this assumptions we will be having this one, that limit as x to the power. Write it down like this: is z to the power alpha a, and this will be f of z as z goes to 0. You can put it absolute value is equal to 0, and limit as z goes to infinity za, and this will be f of z is also equal to 0. So those are two conditions that we have. Two conditions. So now the method of integration is based, so put you like this, method on the following picture. So in this picture, let me make a picture where we are integrating. So I will make a little so put start here, and I make this is my real axis. This is point 0. So here we are not integrating. So integrating is over the black line. So that means this is our line in integration. Add one more axis here. This is my y-axis, and in this case I will do the following. So I will take a small little circle. So this will be k epsilon. So actually this is circle, so call it maybe c epsilon. And I take a big circle here. So it goes like that. Sorry, maybe I need to be more elegant. That's good. That's good. That's good. And then we will start integration here. From this point, so we have this point, and we can put it like that point here, and we go like this way. So call this interval, this way interval, this is interval, and that number is r, so that's a positive side, so this is on the positive side. And on that side will be also, so this is integral a r, but that's on the negative side. And here we will be basically using the definition of the exponential function. So we understand that z to the power a has to be written properly. So let's write it down. Z to the power a is equal e, and this will be a times log, and I'm choosing here not a principal log. This will be log. I denote by z. So this is the log. Let me write it down. Log of z is equal ln of absolute value plus, and this will be I, and I put here argument of z, and argument is chosen from the, okay, where? So that is angle is 0, and this one is angle is 2 pi. So from 0 to 2 pi. From the argument of z belongs to 0 to pi. And you should remember, that means in certain way this line, this black line here is kind of a ambiguous. This means that here we have integration, that let's say logarithm, two values of logarithm from the positive side and then from the negative side. Because on that side, on that line, this will be just simply log of z will be equal just to, so log, so on that line will be log of z, maybe write it down, on x will be just natural logarithm of x. But on that side, it will be, put it like this, log of x on that side, it will be equal ln of x plus I 2 pi, because you made here actually the revolution. So that means you approach this line from the opposite side. So this, you made this particular revolution. So this is 2 pi. So that's how it is on that side. So on the upper side is just a regular logarithm. On the lower side, it is the logarithm plus I to pi. And why I'm talking about it? Because let's denote, let's say one more time. So this is KR. So we decided to call it CR. This one is C epsilon. And then we have this two interval. And the contour, of course, goes like this. So we start that direction. Okay, again. We start this direction. Then we go that direction, this way. And then we arrive here and we go opposite direction, that way. That way. So, okay. So what I'm going to do is I'm going to integrate the function, one second, our function, which will be complex function. So let me write it now. So we will be writing integral over this contour C. Here is RA. So this is the complete contour. So call this one CR, no, epsilon. I'm sorry, this is epsilon. Okay. Epsilon. So this is CR epsilon. And we can write it down, integral, and we have here z to the power a minus 1, and this will be, okay, we should write it down. This will be f of z dz, and then we choose r large enough and epsilon small enough So all the singularities of f of z are inside the contour. CR epsilon. What's happened? Or singularities of f of z are inside CR epsilon. So we can imagine those are singular points. There are many of them. 1, 2, 3. We denote them by zk. Okay, we denote them by zk. So now, in such a case, since all the singularities here, so I can write it down. I know what is the integral. Integral by the residue theorem is 2 pi I sum, and this is sum of for all singular points k. So put here like this k, and then you have here residue of this function za minus 1 f of z zk. So that's this value is not. So we know that it does not depend on epsilon larger than 0 or r larger than 0. Large enough and small enough, of course, like it was mentioned. So we have it, but on the other hand, what do I have here? I can rewrite this integral using the fact that put it here, my c r epsilon is equal, so this is kr, then you have here plus, and this will be k epsilon, but k epsilon is minus, then you have plus, and this one is epsilon r plus, and then you have minus, and this is on positive side, and this one will be er minus on the negative side. So let's check it again. So here we have this one, this is c, I'm using again k, oh my god. Okay, remove it. If I'm going to slow with this, just fast forward. So okay, start it maybe properly like this. Epsilon r positive, then you have plus cr, and this one is positive. Then you go here to minus, and this is epsilon r negative, and then you go back minus c epsilon, and that's how it is. So we are getting here 4 integrals. So first one is the integral from epsilon, and that one is nothing else than r, and here z x just becomes x, so this is x, and that one is maybe write it down using the definition. So that will be like so this will be e, and this will be log. So put it like this, log, and that one will be a minus 1, and this will be log of x, because this is the x, this is f of x dx, and then we look again, that's the definition here, this log here, the log here is on that side, so you see this side here is just simple log, this is our natural logarithm, so we will be changing it, so this is nothing else than ln of x, and on the other side, let's go to the next one, so put here plus, and this will be integral over kr, and this will be again z to the a minus 1. I'm not going to specify it again what it is not necessary, and then we arrived to the other end, but that one is minus, so I should put here minus, and then I put here again integral, and then we are arriving here to the so we are arriving to the to this side. So we go again backward. So this will be negative, and this one will be epsilon r, and this will be negative side. This is also negative, and here we have to put it using the a minus 1. We are on the real line again, but we remember where we are. So we are on that side, and here we have the formula. So this is 2 pi I. So that's 2 pi I. So I can write it down. This logarithm will be ln of x plus I 2 pi, or 2 pi I. 2 pi I. Very good. So then we go next to the small circle. So it again minus. This one is positive. Why did I write negative? This is positive. Sorry. This was correct. This was incorrect. So that one is negative. So this will be k. It's not k. I call it c. Okay. C. So erase. So this is integral c epsilon, and this is c, and this will be z a minus 1 f of z dz. Very good. So now let's simplify it. And let's see what we are getting here. So here, after simplification, the first integral becomes, this is equal epsilon r, and that's just a regular x a minus 1. This will be f of x dx. Very good. Maybe I put together the second one, the third integral, which is of course in this case minus. This will be minus because here we are getting that value. You see, this is in negative orientation, and that refers to the side. So this means related to the value of the logarithm there. So it will be minus, and then I'm having here integral again from epsilon to r, and here I'm having here again, this is the same. This is x a minus 1. That's the first factor, but the second one is simply e to the power a minus 1, and this will be 2 pi I. 2 pi I. So this is the second factor. And then I put here f of x, and dx, and that's my second. And now I have two other integrals, so let's copy them. So this will be integral CR, and this is ZA minus 1, and this will be f of z dz, and minus, and this will be small epsilon ZA minus 1 f of z dz, and I'm claiming the following. So first of all, notice what happens if I take epsilon goes to 0 and r goes to infinity. So this first integral, this one, this is my number 1, becomes simply integral from 0 to infinity x a minus 1 f of x dx. And the second one, the same, except it has a factor, which I can take it out, that value, so I can put it here. This will be 1 minus e, and this will be a minus 1, 2 pi I, and I have this 2. I also claim that the other 2 will give you zeros, will give you zeros. So let's check it out. Maybe I check only one of them, maybe the other one, this one. So let's say like this, I want to compute limit. So limit is 0, 0. As, let's say like this, s is z, maybe write it down like that. Maybe as r goes to infinity of this integral absolute value, CR ZA minus 1 f of z dz, which is smaller equal than limit, and this r goes to infinity, and this is integral CR, and then I put here this inside and change the type of the integral. This is z, and this will be line integral number scalar type. So now that one I can call it again limit as r goes to infinity. Replace that one by maximum, so this will be maximum for z is equal to r of the value, and that one is equal to z a minus 1 minus 1 f of z. Very good. But here I have also times the length of this integral, which is 2 pi r. That's the length of the length of the circle. So the length of the circle is equal the length of the circle CR is equal to 2 pi r. Of course, remember that if you put this one inside this limit, so this is the same as a modulus of z, so I can just simply rewrite it, put here like this. This is 2 pi, this is limit r goes to infinity, and then you have your maximum z is equal to r, and this is z alpha, this alpha, z a, because this gives you 1, this is 1 power, this is a minus 1, altogether is a, and then you have here f of z, and we have the assumption d, and that limit here is equal to 0, so this is 2 pi times 0 is equal to 0. Similarly, you do it again you can do it again for the second integral, but that's exactly the same verification, except the limit is changed to the limit to 0. So these two are there. So immediately let's rewrite the formula that we derived. So we are getting here the formula. We are getting the 2 pi I sum of the zk, all singularities, and then this is residue, and this is function z to the a minus 1, and that one is f of z at the point zk, is equal, this is 1 minus e, and this is a minus 1 2 pi I, and then that's the integral in question, 0 infinity x a minus 1 f of x dx. So I can now immediately, we don't really need to have this assumption about positiveness. No, we don't really need it. So it's just question, no need. We are not using any inequalities here that were required. We just only need to say, but it is possible that say no. Okay, we need it. That we have no singularities. We can assume that it means no singularities, on R plus. So it could be negative, but let's say that's not really necessary. But it's easier to write it. So now, of course, we are getting the formula. So integral from 0 to infinity x to the a minus 1. We derive this formula. So now you have that formula for your application. So if it is easy to apply. So call it like this. This is all over all k over all singularities, and this will be residue. So z a minus 1 f of z at the zk, and this is the required formula. So if you have a formula, so now you need the example. Let's do something simple. I leave you verification that all the conditions are satisfied that we were mentioning. So let me write it down. Compute, and this will be integral equals, and this was from 0 to infinity, and this will be like again, this is principal value of no, there is no principal. Right? This is actually no need. This is actually the actual value of this integral. So that means it is convergent it is convergent under this assumption. So this is x to the power a minus 1, and this is 1 plus x dx, and we assume that a, where is a? Between 0 and 1 probably. One moment, so this is 0 and 1. Let me check. Limit. Okay, so let me check. So we need to have two assumptions. So remember, let's check. Z to alpha, z to a divided by 1 plus z. So in this case, if a is larger than 0, then this will converge to 0. Let's say as z is going to 0. On the other hand, if you take za, and this is 1 plus z, and then you have here that in this case this goes to 0 if of course a is smaller than 1. So that means z goes to infinity. Okay, so I can add the assumption that a is a real number from 0 to 1, and then the conditions required about the limits are clearly satisfied. We just looked at this condition. So okay, let's do the computation. So the solution goes like that. This integral, I can write the answer. Did I write the incorrect formula? Yes. Where is my, why I wrote this incorrect formula here? Yes, divided, so this is correction, by 1 minus e a minus 1 2 pi I, see old h p. We are forgetting to divide. Forgot it. And now when I looked at the solutions, I was feeling like, yes, something is missing. To be sure that we understand what was wrong, let me write the formula again. So this is x a minus 1, 1 plus x is equal, so we have division here. So the first one is 2 pi I, and there is only one residue, and that's a single point, and this is za minus 1 divided by 1 plus z at the point minus 1. Maybe make it nicer. Plan better. A minus 1, 1 plus z minus 1, and the second one is 1 minus e, and that one will be 2 pi I a minus 1, close it. So that's almost done. Now we need to compute this residue, and please remember, always remember that z a minus 1 actually is equal to e, and this is a minus 1, and we have this logarithm that we were using in the definition of this power. So this logarithm, for example, for the value of minus 1 will be equal to I pi. So this will be I pi, and then definitely we can continue. So maybe put it like that. That's here. So I'm getting here that this integral is equal to 2 pi I, and I have here this residue. So this is equal to minus 1 to the power a minus 1. That's the residue value, and that means I have already here that value. So now I have here 1, and this is minus e 2 pi I a minus 1, and then I can continue, and let me simplify it. So this will be like a 2 pi I, and here I'm getting here again that this will be equal to E. Okay, maybe I just simply write it. So this will be E, and this will be a minus 1, and this will be pi I, and here I have here 1 minus E. Put a minus 1 first times 2 pi I. And then what do I have here? I can actually rewrite it a little because I can divide it. So what do I have here? I have it here. This is equal to 2 pi I. I put here 1, and this one divides, so I'm getting here this is equal E to 1 minus a, and this is pi I. I change the sign, so you see this is minus. You see I change it to that one. And then, of course, otherwise I can also change this one here, because I want to write it so this one is actually E, and I put here minus, so E minus, and this is E minus, so this will be minus 1 minus a pi I, because you simplify it. And now I move this 2I over there, so let me write it down. So I'm moving this 2I, so let me write it clearly. This will be like that. This is E 1 minus a pi I minus E minus 1 minus a pi I 2I, and this is pi standing here. And you recognize this is nothing else than pi, and I'm sorry I'm making mistakes to the 2 pi. No. No, correct. Everything is correct. No mistakes. So this one is equal to pi, and we are getting this is sine. And what do I get here? 1 minus a pi. Let me simplify it further. Pi, and this one is sine of pi minus a pi. Oh, and what is sine of that? This is this is sine cos. So this is how much it is. So this is sine of pi, which is 0 minus cosine. This is equal to sine of a pi. Am I right? Let me check it. Sine of pi minus a pi is equal to sine of pi cosine a pi minus cosine of pi sine a pi. This is equal to minus 1. This one is equal to 0. So I'm getting here exactly that value, and we finish it. Wow. Oh, I was nervous. I already made mistake here in the main formula. So that's why I will write this main formula again, in order just to make sure that we will not mix them up like I did it. So this is x a minus 1 f of x dx is equal to pi I, and now I have here denominator 1 minus e, and this is a minus 1 2 pi I here, and then you have here sum of the residues. This is a residue of the function z a minus 1, and this one is f of z at the point zk, all singular points. And remember one thing, that z a minus 1 is equal e a minus 1 logarithm of z, where logarithm is the branch of logarithm with the properties that one plus I, and this is argument of z, which this argument is chosen such that that is belonging to, okay, so this is maybe rated down. This starts here, or 0 goes to the 2 pi, but we understand that we can always possibly include it after going to the limit, something like that, from that side, 2 pi. That's why we are actually achieving this 2 pi here, in this place. So that's it. So we finished. I hope it's not... I took a little longer because I was slow. So just remember, you can always fast forward and look at the answer, what was given, and do all the all the examples yourself. Just practice, and then you find my mistakes. Write me comments. Thank you very much.